So often when we're doing stoichiometry with reactions, we're dealing with reactions in aqueous solution, and we can't just measure things in grams. So for example, copper 2 sulfate aqueous is not the same thing as solid copper 2 sulfate. If we used 50 grams of copper 2 sulfate, that would be very different from using 50 grams of copper 2 sulfate solution, because copper 2 sulfate solution is mostly water, right? But that's the form that most or that many chemical reactants will come in, is aqueous solution. So it's invalid to talk about the mass of an aqueous solution. Instead, we might have, let's say, 50 milliliters of, let's say, 0.25 molar copper 2 sulfate solution. And so if you remember, molarity, capital M, means moles per liter. It tells us the concentration. And so we could easily figure out how many moles we had in 50 milliliters at that concentration. So when working with substances dissolved in water, instead of using grams, we're going to measure them in liters or milliliters, but we also have to know the molarity, right? The capital M, the concentration, because 0.25 molar is very different from 1.0 molar, right? That would be much more, that would be 4 times more moles per liter. This also creates a different set of steps. So for example, if I'm doing this reaction and I want to know how many milliliters of copper 2 sulfate solution I need to combine with a certain number of grams of aluminum, well, there I'm starting with grams of aluminum, and I would have to take that to moles of aluminum, and then I would have to take it to moles of copper 2 sulfate. But since it's a solution, I can't take it to grams of copper 2 sulfate. Instead, I have to take it to liters of that substance. We'll call it substance B. And then we could also take it to milliliters, and I'll show you how that gets done. But it basically just creates an alternate pathway for our problem process. We could also start with milliliters of substance A. So if we want to know how many grams of substance B we need to react with a certain number of milliliters of substance A, we can do that as well. So it just provides us with a couple of different routes that we can take through some of these problems. Okay, so let's take a look at an example here. This is using the same reaction. How many milliliters of 0.45 molar copper 2 sulfate would you need to produce 8.50 grams of solid copper through this reaction? So what I want you to do right now is just start with grams of copper and just take that to moles of copper 2 sulfate. So don't worry about milliliters just yet. Just see if you can take that to moles. And then we'll take it from there. Okay, so I've taken the grams of copper to moles of copper 2 sulfate, and hopefully you were able to get this far as well. But this is where things start to differ a little bit, because I do need to get rid of moles of copper 2 sulfate, but the difference is it's asking me for milliliters, right? It's not asking me for grams because it's an aqueous solution. So I cannot go from moles of my copper 2 sulfate to grams. Instead, I have to go up here to liters because it's an aqueous solution. And again, my relationship between moles and liters is where that molarity comes in, right? That means 0.450 moles per 1 liter. And so now I'm at liters, and I'm very close to having the unit that I need for my final answer. And so that is simply going to be liters to milliliters. So liters of CuSO4 taken to milliliters just means multiplying by 1,000. And there I am done, and I'm ready to calculate. All right, so I got 297 milliliters of CuSO4. And it's hard to do a mental check with grams and milliliters and figure out if that makes sense, but It does make sense. Milliliters are so small that even though that's a large number, it is reasonable to expect almost 300 milliliters of copper 2 sulfate needed. Okay, the next question says, what is the concentration of the aluminum sulfate product? Okay, so this is a little different. Let me get rid of some of this mess. We are now trying to figure out the concentration, the molarity, or the moles per liter of our product. Now, keep in mind in this reaction we have an aqueous solution and a solid on each side of the reaction. So we're putting together, in this case, 297 milliliters or 0.297 liters of the copper 2 sulfate with some solid aluminum. And we don't really know what that mass is, but we can assume it's not a huge mass, so we'll just draw some little specks of solid aluminum maybe sitting at the bottom of the beaker. And then there's a single replacement reaction that happens and the aluminum replaces the copper, and now we're going to have now the little specks at the bottom represent copper. And the solution, the 0.297 liters, would be my aqueous product, my aluminum sulfate. So now this volume no longer represents my volume of reactant. After the reaction is over, it is now the volume of my aluminum sulfate. So I'm going to go ahead and say that if I want to know the molarity of my aluminum sulfate, that is simply going to be equal to my moles of aluminum sulfate, which I don't currently know, but I'm just going to put that on the top, divided by my liters, which I do know because it's the 0.297 liters of aqueous solution that I started with. All right, so if I can figure out the moles, I've got my answer. And we should be able to do that once again, starting with my 8.5 grams of copper, but this time I'm just going to go to moles of aluminum sulfate. So see if you can figure out the moles of aluminum sulfate. Okay, so there it is. I started once again with my 8.50 grams of copper. I converted that this time to moles of aluminum sulfate. Again, using the balanced equation, there was a 1 in front of aluminum sulfate. And then I got my answer, which was 0.0446 moles of aluminum sulfate, which I can then just plug in right here over my liters to get my answer. And of course, I didn't leave myself enough room for my answer, but it should be 0.150. Maybe we'll do that in a different color. That would be molar aluminum sulfate. And that is, just our moles per liter. All right, let's go ahead and tackle this next one. How many grams of nickel 2 hydroxide would you expect to produce by reacting 450 milliliters of 0.35 molar potassium hydroxide with sufficient amount of nickel 2 nitrate? Go ahead and see if you can come up with a balanced equation. Okay, so there we go. There's our balanced equation. Hopefully you came up with something like that. Now let's get to the actual stoichiometry. It wants to know grams of nickel 2 hydroxide. So we're looking for grams of this stuff, right? And we're starting with milliliters of 0.35 molar KOH. So see if you can set this one up. Go ahead and start with your 450 milliliters of KOH. Use the molarity to take that all the way, or to moles of KOH, and then eventually all the way to grams of nickel 2 hydroxide. Go ahead and give that one a try. All right, so there it is. I started with my 450 milliliters of KOH. I took that to liters, then to moles using the molarity. Then using the balanced equation, I took that from moles of KOH to moles of nickel 2 hydroxide. And then finally using the periodic table, I took it to grams and got 7.30. All right, another question. How many milliliters of the other reactant would be needed to perform this reaction? So this time we're still starting with milliliters of KOH. but instead of going to grams of something, we're going to go to milliliters of our NiNO32. So go ahead and give that one a shot. All right, so there it is. Once again, the process started the same way. Everything was the same up until right here when we were going to moles of nickel 2 nitrate instead of nickel 2 hydroxide, although it is still a 1:2 ratio. And then here, this is different because we're going to go to liters instead of grams. And that I just used my molarity of 0.25 moles per 1 liter. So that's why my 0.25 went on the bottom. And then finally, just multiply by 1,000, and I get 315. Okay, last one. Calculate the molarity of the aqueous product from this reaction. Assume the formation of the precipitate has no effect on volume. So I'm going to give you a big hint here. Earlier, when we just had one aqueous solution going into the reaction, we just used that volume as the volume of the product. Well, in this case, we actually have two volumes going into this reaction. And those two volumes are essentially still going to be there in the end. In other words, I'm going to be combining, if I want to draw my beaker here where the reaction is happening, 450 milliliters or 0.45 liters of KOH, and I'm going to be combining that with 315 milliliters that I just calculated, or 0.315 liters of my other ingredient, and my product is going to be, is going to take up this whole space. So the volume of my aqueous product, which in this case is my potassium nitrate, is going to be the sum of those two volumes. So that is just it's a matter of adding up those two volumes, but we also do need to figure out our moles of potassium nitrate as well so we can get the molarity. So go ahead and give that one a shot. Okay, so I went ahead and started with 0.45 liters of KOH, and I skipped the step of going from milliliters to liters because it's just dividing by 1,000. Plus, I already established that was, 450 milliliters is 0.45 liters. So I started there, and I took it to moles of KOH and then to moles of my aqueous product, which happens to be potassium nitrate. You could have done this starting with 0.315 liters of nickel 2 nitrate. It should give you the same answer. You could even start with 7.30 grams of nickel 2 hydroxide, and it should give you the same answer. Either way we do it, using stoichiometry, we get the same number of moles of potassium nitrate, 0.158. And the very last step, because it's asking me for a molarity, is to divide that number of moles by my number of liters, which I already said is the sum of the two liters of ingredients. So 0.315 plus 0.45 liters. And if I add those together in parentheses on the calculator and have those in my denominator, I should end up with a molarity of 0.206 molar potassium nitrate. All right, so that is solution stoichiometry. We'll get plenty more practice in class and in the lab.